Graphing square root functions and inequalities. This is section 6.3 in the Glencoe textbook. We've spent a lot of time this year graphing y equals x squared, the parent function of the quadratics. We've recently seen that the inverse of this would be two pieces, y equals the square root of x and y equals the negative square root of x. Our focus is going to be this red piece here. We're going to be transforming it, which means reflecting it, stretching it, translating it, all as we graph it. When you explore the function with a, h, and k, we can see that hk is the endpoint. It's either the minimum or the maximum, and in the case of the parent function, it's the minimum value of our curve, which goes on infinitely only in one direction. Just as we've seen before, h tells us how far we move to the right or left, k tells us how many units up or down, and a tells us the stretch and the direction of our function. Unlike other functions we've worked with in the past, we have a restricted domain when we graph square root functions. What that means is that our function starts at a certain point, so we cannot choose any x values we want. If we look at these two square root functions, we see that we have the same domain, x is greater than or equal to 0. Let's think about why that is. We know that in order to take a square root, we can take a square root of 0 and any positive number. So since in both cases the radicand is just x, we're allowed to put in 0 and all of our positive numbers for x. Let's look at a case where that would not be the case. In this function, if I put in 0 or a positive 1 or even positive 1.99, I would be taking the square root of a negative number, and therefore I would not be allowed to do it. That makes sense then that our domain here is x is greater than or equal to 2. In order to figure out what x values we are allowed to put into our table of values, we want to set the entire radicand greater than or equal to 0. When I set my radicand greater than or equal to 0, as I did over to the side, then I know what values I'm even allowed to put in for my domain. However, choosing these values for my domain will not make my work very easy. For example, I would have to take the square root of 4 minus 2, or the square root of 2. That's not so easy to graph. So I want to be logical about what numbers I pick so that I can get a nice, friendly output. Also, although these arrows aren't drawn in, these square root functions continue infinitely in one direction. Now we're going to actually graph ourselves. So here are our steps. First, we want to find that endpoint. We're going to find the minimum or the maximum ordered pair by setting the radicand equal to 0 and then finding the y-coordinate. We're going to figure out the possible domain values by setting the radicand greater than or equal to 0. We can actually combine those steps and sort of just do the second step. Then we make a table, we plot the ordered pairs, and we connect them. Pretty soon we're also going to be graphing inequalities. Then we'd have to think about a few key things. Do we have a dotted or solid line? Do we shade above or below? And do we have an open or a closed circle on our endpoint? Let's do example 7. The first thing we need to know is check the domain. So in order to check the domain, we're going to set the radicand greater than or equal to 0. In this case, it's quite simple. X is greater than or equal to 0. Then we want to make a table of values where we have x and we have y, and we have a spot in the middle for work. Now, we know that we could put 0, 1, 2, 3, 4, etc. into our input column. However, since we're taking the square root of x, I'm going to choose numbers that are easier for me to take the square root of x, so I chose the perfect squares. I'll show my work in the middle and get my ordered pairs. Now that I've shown my work and got my ordered pairs, I've graphed them on the graph and I need to connect them to make my square root function. Don't forget that you should have an arrow going in one direction. We should always check to make sure that what we've graphed makes sense. We can see that we were supposed to shift our parent function down 3 units, which we have done, and we can see that we should be scrunched because we are multiplying everything by a coefficient of 1/2. So rather than us go up 1 and over 1, or from this endpoint up 2 and over 4, we can see that we're doing half as much. Now the reason why I know those ratios is because I can picture my quadratic, and I know that normally I'd start at 0, 0 for x squared. I'd go over to 1, 1, and I'd go over to 2, 4. Now let's talk about the domain and range. The key to identifying the domain and range is to use this endpoint here. I can see that my domain will never go below that point, and my range will never go below that point. Therefore, my domain, which we've already talked about, is x is greater than or equal to 0, and my range is y is greater than or equal to -3. The point 0, -3 is a solution to the function because that endpoint is included. I can take the square root of 0, and so if I plug 0 into my function, I get -3 out as my output. It's a point on our line. Now, when we think about the range, if we had a negative a value and our square root function had a different concavity, then we would have a maximum instead of a minimum. Let's do one more example together. This is an inequality. Because we have a greater than symbol that is not inclusive, that tells us that we're going to have a dotted line and an open circle at our end. We also know that we're going to have some shading. So let's start with the first step. We can first predict how this is going to look. We can see that we have a negative a value, so we know that we will be concave up. Our curve is going to curve down. And we can see that we're going to shift our endpoint side to side, but we are not going to shift it up and down because our k value is 0. To find our domain, I set the radicand, which is 3x minus 2, greater than or equal to 0, because again, we can take the square root of 0 and any positive number, but we cannot take the square root of anything negative. Now I'll make a table of values. I have to put my endpoint, or x equals 2/3, into my table of values because I know that I need the endpoint for my graph. After that, I strategically thought about what values for x will make this radicand into a perfect square. So if x is 1, then the radicand is 1. If x is 2, then the radicand is 4. If x is 6, then the radicand is 16. So I purposely chose numbers that would be both easy for me to graph their input and their output. I've completed my table, and I've plotted my points on the graph. Now we need to apply what we wrote down before. We know that this should be a dotted line, not a solid line, because our inequality is not inclusive. We still need an arrow, and we need an open circle at the end here. As long as the dots all along the line do not look like you are plotting those points, and it's clear that it's a dotted line, you don't need open circles along the way, because the dotted line implies that that entire line is open circles. Then we have to think about, well, are we shading above or below the line? We're shading, in this case, above the line, because it says y is greater than or equal to our line, or our negative square root of 3x minus 2. Now we also could always test a point, and it's a good idea to do so. So we could test the point 10, 0, for example. We'd have 0 is greater than negative square root of 28. We know that that's going to end up being a negative number, so 0 is greater than our negative number, and therefore we've shaded the same region, or the correct region. Now because of the tools on this software, my line looks like it goes all the way to 0, but keep in mind that really it is only shaded up to above 2/3. Now, the points on that line are actually included in the domain, even though the endpoint is not. If we were to test the points above, so x is 2/3 and y is a different value above 0, that would in fact work. And we're going to test that right now on the part here that says circle the points that are part of the solution set. So one way to do this would be to look on the graph, and we can see that 2/3 0 is an open circle, so it is not a solution. And 2/3 2 is in fact shaded. It's part of the shaded region, so it is a solution. But we want to always double check it by actually testing the point, just in case we made a mistake on the graph. When we test it, we can see that 0 is not greater than 0, but 2 is greater than 0, and therefore only the point on the right works. If we want to state what the domain and range are, for this case, our domain is x is greater than or equal to 2/3, because even though we have an open circle, all of the points above that are part of this relation. It's not a function because we have multiple values with the same x coordinate. Our range then is going to be all real numbers, or y equals all real numbers. And that's because if you think about it, this line is going to continue to go more and more negative as x increases, and we already have hit all of the positive y values above that. Now it's your turn to practice. In the meantime, I hope you enjoy some Radicals humor. Have a great day.